Hello, welcome to lecture 11 or CS11. So this lecture is going to be slightly different from all of the lectures you've seen so far, lectures 2 through 10, which are the actual coverage of the hope. 11 is more of a meta lecture in that it might help you if you want to, debug, as we'll see later, some of your solutions that you make when you're taking either a hope or a future lab exercise. So we're going to go through some things that might help you test your programs better, basically. So let's start with, are you practicing? So I don't know how near the hope is going to be once you watch this video, but by now, hopefully, you have gone through most, if not all, of the practice sets available to you. So if you're watching this after the mock hope is also something that you can use to prepare. Aside from these 1, 2, 3, 4, 5, 6, 12 sets that we have over here. So yeah, please practice if you want to pass or do well in the hope. But yeah, we will move to lecture 11. Okay, so as we've seen so far, with all of the lectures we've had so far, your computer can, compute stuff. You can give it pretty big numbers, and it can multiply them for you. You see that we can define functions that give you some values, and you can call those functions. So it's great at computing stuff, but if you think about it, that's only useful if you can give it something to compute and see what your computer computes. So I hope that makes sense. Aside from getting values like these, hopefully there's a way, aside from interactive mode, to actually see what's happening aside from just functions. And let's see, io.type. Aside from just making functions, then printing out the values of those functions, hopefully we have other ways of getting input primarily, since for output we can already see that we'll actually already know how to do output by printing them out. But yeah, input output. So another way to look at this is that a computer inside a vacuum is pretty useless. If it can compute stuff, but if you can't feed inputs into your computer, then it doesn't really have anything to compute in the first place. So a computer inside a black hole is useless. Okay, so for this first section of this lecture, we're going to look at some ways you can get input and output from a program, in a Python program. So again, you already actually know how to output something by printing. So that leaves input for now. Okay, so for input, we have a dedicated function called input. So let me remove all of this. Input. So what does this function do? So what it does is get some line of input from the user. So here I have an example. Line is equal to input. What I'm doing here is something. What I am doing here is I'm asserting that this line is a string. I'm essentially checking or asserting that the type of line is equal to string, or line is a string. And what I'm doing here is I am printing the length of the line. So here, alright, let me try to run this program. So if we try to run it, we see that it kind of hangs. It's staying there and it's not doing anything. The reason it's like that is because it's waiting for input from the user. So we can input something over here, 11, and what we see here is after we press enter, so I give it the input, then I press enter, it says the input line has 2 characters. So as you can see here, it reads this line as a string. So if I give it 1, 2, we see that it has 6 characters. It doesn't treat this as a tuple, it treats this line as a string. So 1 character, 2 characters, 3, 4, 5, and 6. Which is why it tells us that it sees 6 characters. Okay, let's go back to this line over here. A while ago I said that this is essentially the same thing as saying type of line is equal to string. For purposes we will see much later in CS11, most of the time you want to express this as this instead. This instance checks or returns a boolean, true or false, depending on whether some value is of some type. So let's try to look at that over here. If I say isInstance 1 integer, we get true. If I turn this integer to a string instead, I get false. So it's essentially the same thing as checking whether type of int is 1 or type of int is, not type of int, type of 1 is int, or type of 1 is string. So it's kind of the same thing. There are a few subtle differences, which is also the reason why using this is better instead. But for now, you don't really need to worry about that difference. All you need to know is use isInstance instead of double equals with type. Okay, so we see here that we passed nothing into input. We can actually give it something. So here we can, let's copy these 2 lines. It's getting a name and it's printing out that name. So if I try to run this, it's asking for my name, I give it my name, and it greets me with hello there. So it's asking us, what if, or why is there a space at the end of this string? So what happens if instead of ending with a space, I end with the question mark of the question? If we try this, we see that what we have here is that the start of where we can input comes directly after the string that we put inside the input function over here. In terms of, well, user interface, this looks objectively uglier than if we put a space at the end instead. So if you want to do something like this, you would usually put a space at the end of the question. Okay, so that's input. So here you can also do things like this. So if you want to get a actual number, you can convert whatever the input is to some type that you want and assign that to a variable. So for this example over here, I have this. So just to demonstrate that this is actually an integer, so let's say twice of your age is 2 times age. So if I try to run this, my name is Daryl. See, my name is Daryl. I am, well, age reveal, but I give it my age and it gives, well, we see that it treats this, whatever I put it, as an integer since I converted it to an integer over here. If I didn't convert this to an integer, I just use input as usual. If I tried to run this, I enter my name, I enter my age, we see that it treats the 21 here as a string. So this 21 becomes 2121, which is not what we want. So make sure you convert them to the right type. Here I'm converting it to 21 as an integer. which is why I get the right value here. Okay, so you might be wondering, why introduce input only now? I'm not sure about what you've experienced. Maybe in your high school classes, one of the first things you were introduced to is how to get input from the user. Why is it that in CS11, in our Intro to Programming course, we're only introducing input, mainly input, in lecture 11 instead of lecture 2 or something? We'll see the reason pretty soon actually. After the first hope, some of the first few lectures after the first hope are going to go over why we only went over input and output until now. Why we only went over input and output at this point in the course. So for now, the gist of the reason is that they're kind of different in a sense from all of the things that we're used to so far. Let me give a sneak peek. So let's say I have a function, return x. U of x returns x, but I print x over here. So these are two functions that, well, kind of do the same thing. They both return the same value, but this g has a print inside of it. Alright, so what happens if I call f of 2 twice? If I call f of 2 twice, I get nothing since I'm not printing out these values. If I call g of 2 twice, two things get printed out. So print is what we call a side effect, and essentially side effects are a different way of or part of a different way of thinking, which we will go over in the first few lectures after the first hope. So yeah, that's just a sneak peek. As for print, outputting, we taught print early because it's actually pretty useful for debugging your programs. So if you want to figure out what your function is doing, y is equal to x to the 2 plus 11 times x minus some gibberish, you would normally want to know whatever this value is first before you go return it. So that's how prints can be useful if you want to debug your program. Okay, so now that we've introduced input and output, input and print, for now, we strongly recommend separating the I/O part from the core logic of the program. What do we mean by that? So let's say you have this function over here. Let me delete all of these, and I have these three functions over here. Let's say this is what OJ is asking me to do. Normally, what you submit to OJ is just this part of the solution. You have some function and maybe it uses some helper functions like these. So what we recommend is separating the solution part, what you would normally submit to OJ, from the input-output part. So the input and output here is separate from all of the function definitions you see over here. This is separation of concerns, basically. Okay, so another way to go about this is you take all of this input and output and put it into its own function. Say main, and here you call main. So here I'm putting the I/O part inside a main function. Then to run my program, all I do is call this main function. So this looks a bit less cluttered compared to if you just put all of this stuff over here. At least here, you know that all of your input and output is in one place, the main function. There's a slightly better way of writing this. So there's this weird line over here. We won't go exactly over what this line is doing. You might want to search this up instead, or ask us in the Discord server. The gist is for pretty big programs or more complex programs, you might want to write something like this instead of just putting main over here. But for, say, solving OJ problems, this is not something you have to worry about that much. Okay, so that's input and output. So again, try to separate your input-output from the actual functions you're implementing. So let us now move on to a slightly different thing. So we have this thing called exceptions in Python. You've already encountered quite a lot of exceptions actually. So you have these exceptions. Hopefully these are familiar to you. You might have seen them in the lab lectures or the lectures. So what are exceptions? Well, in Python, exceptions occur when something unexpected happens. Or in other words, you do something illegal. So in Python, there are legal things and illegal things. So for example, you won't go over how to actually do these things yet, but one thing you can do with Python is open a file. You know what a file is from Lab Lecture 0. It's pretty much everything that we've been working with so far, like this io.py file. It opens a file, it reads the contents of that file, it does something, and it writes to another file. Okay, so let's say we have a program that does something like this. What are some things that can go wrong when we have a program like this? Well, one thing is that the file that we're trying to open doesn't actually exist. So you can actually kind of see that if I try to open some random file that doesn't exist, in Bash it tells you something like this. In Python, the equivalent would be an exception. So another possible problem is that the contents are gibberish. So for example, it expects numbers like, let's say expected, or let's put that inside a text file instead. So it expects numbers like this, but what it actually sees, actual, is something like this. So instead of numbers, it sees letters. So malformed contents. So maybe it sees well-formed contents, but for some reason the computation failed. By computation failed, we mean stuff like dividing by 0. Remember that dividing by 0 is illegal in Python. Or it sees non-integers or floats when it expects integers. And another possible problem is it cannot write to a file. So if it tries to write and your computer already has a lot of files and has no more storage, then of course that's another way in which your program can fail. Alright, let us go back to interactive mode and let's see some of these exceptions that we've already seen. So one example is index out of bounds. So if I have a string and I try to index it at some ridiculous index, I'm going to get an index error. So whatever index I'm giving it is way beyond the range of indices that this string supports. I can also have a type error. So let's say I have 11, I'm adding a number with a string. This is a type error since, as you hopefully have seen in lecture 0, or lab lecture 0, you can't add a number with a string. What else? A name error. So let's say I have x is equal to 2, but for some reason I'm printing out z. This is a name error, since where on earth does this z come from? A syntax error. So there are some things that you can't do in Python. One of the first things he went over in lab lecture 0 is that doing stuff like this is not possible, since you have to not put spaces in between your numbers. So syntax error. What other errors do we have? So we can also have attribute errors. So let's say you have a string. Let's say you have a string. Then you try to do some function on it that doesn't actually exist. So if function that exists, for example, is upper, so it turns all letters into uppercase. But if you invent some function like this, you'll get what we call an attribute error. So you can't have a attribute like nerf on strings like this. Okay, value error. We see these when we're converting from one type to another type. So let's say I want to convert 11 into an integer. That works since we can convert 11 into an integer. If we try to convert this instead, we can't convert a string into an integer, which is why we get a value error. An assertion error is if we try to assert nonsense. So 2 plus 2 is equal to 5. We get an assertion error, since obviously this has to be 4. So in more complex cases, using our example from a while ago, there's also something called an OS or operating system error. If, for example, we try to open a file that doesn't exist. Well, actually, I can try to demonstrate that right now. Let's see, exceptions.py, oops. Then I try to open a file that doesn't exist. As file, then do something. Print I. Alright, so if I try to run this file, we see that we get a file not found error. This is actually a special kind of OS error. As the name suggests, it's saying that it can't see a file called archive.txt. So there are lots of exceptions out there. You can always check the documentation for all the exceptions you can run into. I don't know, you might want to make this some sort of bucket list or something. Okay, so that brings us to the question. Why do we have exceptions in the first place? What's the point of having exceptions? So why is it that if we do something like this, Python complains at us? Well, that's kind of asking, why are some things illegal in Python? And well, I guess the answer is kind of obvious. There are things that should be illegal in a programming language, especially if you're doing black magic like this. So I guess the counter argument to why not exceptions is, well, you provide some ways that you would handle weird cases like these. So what are some things, let's say exceptions don't exist, what could you do otherwise? Okay, let's say you have a function and you pass in some invalid value. Okay, let's say I have a function here that's supposed to take in a number and return that number plus 1. Okay, pretty simple function. So let's say an invalid value was passed. So here, a normal way to call this function would be f of 5 or something. if the user inputs something that you don't expect, let's say haha, one way you could handle that is, well, ignore. So let's say if not is instance, x integer, return, let's say -10 or something. Otherwise, return what you would expect. If I try to print these two things, what I would get is going to be, let me try to run that, 6 and -10. So if you try to do this, your user might get pretty confused. I have a function, and for some reason, it is giving me random values like -10. So that's kind of the reason why doing this might not be a good idea. And we actually have a principle for that. It's called the principle of least surprise. You want to not surprise your users as much as possible. Or in other words, don't try to do magic. Try to do what your user expects you to do. In this case, you're returning some random value if the input is illegal, which might surprise the user. So don't do stuff like this. Okay, so that's one way you can try to do things. Another important thing is that the user in all of these sentences over here, that's not limited to other people. That could also be you, the person who made the function. Let's say 1 month down the line, you go back to this program, you're trying to print out these values. 1 month later. Okay. Then you try to run your program. More often than not, after a month, several months, you too are going to get weirded out if you see random outputs like these. So try not to surprise yourself, basically. Okay. What is another way we can try to work around exceptions? We can predict what the caller meant. So maybe if it's not an instance of an integer, maybe they input -5 instead, we can return int x plus 1. We can convert it to an integer first, then after that is where we add +1. So if you try to run these would actually work. Okay, that's nice and all, but if I try to input some random stuff over here, again, if we try to run that, we will run into problems. So again, this violates not only the principle of least surprise, it actually also violates keep it simple stupid. Since if you have to worry about how you're going to handle invalid inputs, that's going to make your implementation of the function much more complex. So yeah, and yeah, the user is going to get pretty confused. Sometimes it works as expected, f of -5, sometimes things don't go as planned. And again, just like with the previous thing, the user here could be yourself. So 1 month later down the line, you might end up confusing yourself, and you don't want to do that. You might hurt yourself in confusion. So yeah, try not to predict what the user meant. Okay, what are other ways we can handle this? You could, instead of trying to fix things, you could just return none. So if you do something illegal, I don't really care about what you input, you're getting none instead of x plus 1. So here, I would get 6, then 2 nones, since these two inputs are illegal. Is this a better alternative? Well, you could say that, yeah, it might not cause issues yet. If it's illegal, then, well, you have to deal with none instead of an actual value. This might be fine until you, for example, in more complex programs, it might accidentally do stuff like this. So once you reach stuff like this, you might wonder why things like these are not working. So here, the example we have is still pretty tame, but as your program gets more and more complex, hopefully you can imagine that it gets harder and harder to debug. So the worst case is that the user might not even realize that it's not their issue, it's your issue. So it's not their function that is causing the problem, it's your function that's causing the problem. So once again, the user here could be you. So in simple terms, you might end up gaslighting yourself. So don't try to return special values if you don't want to gaslight yourself. Okay? Alright. So, what's another thing we can do? Well, I guess by now you can realize that these previous solutions don't really work. So, well, if we raise an exception, what benefit do we get from that? Okay, so we give up on not using exceptions. If we use an exception, so use an exception, what's going to happen here? Well, the user is going to immediately see where the problem is. And once they can see that, it's a lot easier to debug once you know the root cause of a problem. And in addition to that, exceptions have a type. We've seen all the different kinds of exceptions a while ago. They also usually have a message attached to them, which can help us debug faster. Okay, so again, yeah, for our purposes in CS11, exceptions are going to be the most helpful out of all of these quote-unquote solutions. So yeah, let us do this. Let me take this function. Oops. So how do you actually, use an exception? That is where the raise statement comes in. Oops. So here I have this function, and it checks whether x is equal to 420. If it's equal to 420, it returns 420 squared. Otherwise, it raises an error. So raise here is how we make an error. We raise a value error, and inside the value error, we say, I do not like that number. So if I try to call, say I call print my function 420, since it follows the if branch over here, it's going to return 420 squared, or this number. If I don't put in 420, let's say I put in 11, I'm going to get a value error since I raised a value error over here. And we see here, it says, I don't like the number you gave me, which is what we put over here. You can, of course, put other strings that we want. So if I make the same call, we get this error message that we put over here. Okay, so calling anything other than, I should change this, anything other than, my function 420 is going to raise a value error. So depending on where you run your program, the error message is going to look like this. You start with what we call a traceback. Your program is tracing back whatever happened to your disaster of a function call. So trace back, it's going to see where the exception happened. So in this file and in this particular line, we see that a value error was raised, and we see the value error over here. So this is what we call the trace of an exception. Okay, so hopefully, as you can tell, error messages should point you to whatever is going wrong. So please try to learn how to, or get used to, reading error messages like these. So at least for stuff like these, what's important is, first of all, where the exception is happening, the file, the line, the function, as well as what kind of error you're getting. So try to parse the information that's going to be helpful in debugging. Okay, so aside from raising exceptions, so you want to complain by raising an exception, how do we handle those? So okay, your function call raises an exception. What do we do about that? Cry about it? Well, we can actually do something about it. And for that, we have what we call a try except statement. So let me use the same function over here. So a try except statement is, as the name suggests, inside the try, you're going to try something. So I'm going to try printing out my function at 11. And what the except is for is to handle the case where this raises an error. So if I put here some string except value error, what this is saying is that if a value errors when I try, if I get a value error when I try doing this, I will do this instead of pursuing this. So if I try this, we see that we don't get the same trace from a while ago. All we get is the sad message over here. So what it's doing is kind of canceling what you have here. Okay, so you're not limited to doing this. You can also have multiple except branches. So except type error, for example, type error. You can do something, value error, do something else. So you can do something like this. Okay. So what if this part actually goes properly? So if I give it 420 instead, we see here that we get 176 per 100 as we expect. So we have something called an else. This is the same else from if else. So try a bunch of excepts and an else. This is kind of analogous to if, elif, a bunch of elifs, then else at the end. So what is this else for? If we can already print out the result here, why do we even have this else over here? Generally, if you're going to use try excepts, a series of try except blocks, it's good practice to isolate the part that can error out as much as possible. So instead of already printing out this function call, try to assign this to a variable. Then here is where you print out the result. So these are two different things, well, slightly different things. This one is eager and it prints out the result already. This one isolates the function call that might error into the try block. Usually it's better to do this instead of this. That's why they added the else part to try except, since if you have this instead, it might be harder to debug where things actually went wrong. So to illustrate this, let's say I had something like this. Okay. If I comment this out, and let's have this. So I run this, and I see that I get a type error. So can only concatenate a string to a string, since I can't concatenate a string to an integer. What if I do this? If I try to run that again, I get a womp womp, since, well, I have an except over here. So what this does, actually let me bring back the type error over here. Print type error, then this message, then value error, then this message. Alright, so here and here. Okay, we get these corresponding errors. The reason we prefer isolating this over what we have here, well, the better way to write this would be something like, start with this part that can error. So try x is my function for 20. Okay, except this can raise a value error. So except value error, print, well, let's just take this. Okay, the else is where we try printing 3 plus this. So in here, you can actually nest try excepts. So try printing this, except type error. That's where you put this message. Else this. Okay? So the difference between this and this is that in here we basically put an entire disaster over here. Here we're being careful about where we put things that are potentially disasters. Here we're just combining all of those possible disasters into one line. It can be harder to debug if everything is in one line compared to if you're approaching it one piece at a time. Since if this part already fails, you already know that you have a value error on your hands. Okay. So as a catch-all for the errors at the end here, after a bunch of excepts, you can usually put except exception. Exception is kind of all-encompassing, so some exception. Then you can put whatever you have over here. So if I have some weird error that doesn't appear in these excepts, we can see that it defaults to the exception over here. Okay, so that's the default exception. Again, these are blocks. As you know, we can nest blocks. So as I showed over here, inside the else part, we can put another series of try excepts. Okay, so this example here is pretty useless, but it's just to illustrate the fact that you can put blocks inside blocks, which we should already know from one of the earlier lectures. Okay, let's move on to a more practical example. I want a function that returns a real root of a quadratic expression over here. If there are no real roots, return none. Alright, so for this, hopefully you realize that to solve this, we just have to use the quadratic formula. So b squared minus negative b plus minus this all over 2a. For our purposes, let's just use the positive sign. Alright, this is one way to do it. So let me go over here. Let me go to a separate file, root.py. So here, what I am doing is I have two functions, one to get the real root and another one to get the discriminant. What this is doing is it's using the square root function from the math module. So you might know from previous lectures, I keep doing something like from decorators, import everything. Actually, let me copy decorators here so that this doesn't complain. Let me reopen the file. Okay, so by importing, we're getting some function or functions from some module. We call these things modules. So here what I'm doing is getting the square root and using that inside this function. Now, is this correct? So this is the built-in square root from the math library. So the problem with this is that if I try to get real root, let's say of something with a negative discriminant, so if b is 1, a is 1, and c is also 1, if I try to run this, oops, Python 3, root, I get a value error, or math domain error. Essentially, it's saying negative numbers are not in the domain of the square root function. So that fails. So let's fix that. Again, our problem statement tells us no real roots, return none. Okay, so if d is less than 0, then too bad, we're getting none. Otherwise, return this. Okay, so now if I try to call that and I wrap that around a print, I see that if I try to print that out, I get none, as I expect. So are we satisfied with this? Well, that works. Okay, and yeah, since this follows what the function wants us to do, this is pretty much fine. But can we do better? Let's look at this. So here I have a slightly different implementation. Instead of an if-else, I am doing something like this. So get the discriminant. I'm trying to return this. And if I get the same domain error thing, that's what I put inside this except block, return none. So this is kind of the same idea, but I'm using a try except instead. In the except, I indicate a value error. So if I try to do this, I get none again. So this also kind of works. Now, what's the advantage of this over the previous implementation, yung if-else? Here, you don't really have to determine yourself what the exact condition of failure is. In attempt 2, we explicitly indicated yung d is less than 0. If you're unsure about the failure condition, or if you're just too lazy to write it out, you can always just delegate the error catching part to a try except. So yeah, just try it, then handle the case where it doesn't work. This is yet another principle. Or for EAFP. What does EAFP mean? It's easier to ask for forgiveness than beg for permission. Or than permission. So easier to ask for forgiveness. So in this example, we're asking for forgiveness inside this except block, rather than asking for permission via if d is less than 0. So it's better to ask for forgiveness rather than to beg for permission. Okay, so can we do even better? Let's look at this. What is the main difference here? A while ago, I mentioned that you should isolate the part that can error out as much as possible. And that is what this solution does. Here, it's isolating the part that can error. So square root of d. So here, it has square root of d is square root of d. It moves this part to the else statement. So if everything goes well, I can compute the root like this. So here, we're isolating the part that can square root, which is good practice. So only the function call that can cause issues is in the try block. Well, actually, there's another part here that can error out, and where you can put another series of try excepts. Try to figure it out. Where can you add another set of try excepts for this part? Okay, so how about another attempt? So this is pretty much the same thing actually, except instead of inside the except block, instead of returning none, if it's okay to change the behavior, I can raise an exception instead. Raise value error, then the polynomial has no real roots. So inside the except, I'm raising an error. So you can think of it as I'm kind of chaining errors over here. If I run this, I get value error, then whatever error message I gave it. Okay. So let us try to judge this attempt. Well, it's good since it's still asking for forgiveness rather than begging for permission. And a caveat of this is that it's the user, whoever is using the real root function, that also has to ask for forgiveness. What do I mean by that? So a while ago, well, when we returned none here, all we have to do is, kind of handle the case where this evaluates to none. If instead we put an raise exception here, raise exception, exception, the polynomial has no real roots. Since this function can now raise an error, now the user of real root has to put this call into a try block. It can't just assume that this is either a value or 0 or none. So that's a subtle difference. But yeah, depending on what you want, and you can either do this or what we did a while ago, just return none over here. Okay, so there's a slightly different way to do this part, which is this. So here, the only part that changed is that instead of doing this, what I'm doing here is accept value error as ex, then what I'm doing here is raise a value error from ex. What on earth is this syntax? Okay, let us recall what we got when we only had this. If I try to run that, I get this exception. Okay. Oh, let me change this to value error. So if I try to run this, I get a value error. If I write it like this, as ex from ex, and I run that, so this is the traceback that I got. So what you see here is this message here. The above exception was the direct cause of the following exception. So you can clearly see that it's explicitly telling you where it's going wrong. So that's the main difference. So the trace is clearer, but for now you don't really have to force yourself to use this. You can do what we did for attempt 4, where we returned none here, or attempt 5, where we did this, the erasing a error. Okay, so that is exceptions so far. Alright, so back, if we combine this with input and output, we can have something like this. We're asking for the name and the age, and we're printing out this sort of stuff. So here we're checking if they input a valid age. They didn't just input banana or something. So here, if we see that the user input something illegal, we catch that value error from this int age raw, and we say that that's not a valid age. Okay, so this is actually pretty bad. Why is that bad? Again, when it comes to tries and accepts, you want to isolate the part that can error out as much as possible. So what that means is that instead of writing this, we should write something like this instead. So here, I have pretty much the same lines of code, except I isolate the conversion to an integer inside the try block. So here, I see that these parts are now separate. The input age is here now, and the printing of the illegal age is now here. And the printing of the legal age is in the else block. So again, try to isolate the part that can raise an exception as much as possible. Alright, that's for exceptions. So you might be wondering, what is the difference between an exception and an assertion? So we know that if we fail an assertion, that's a kind of exception. So if we have, let's say, assert 1 plus 1 is equal to 11, this is an assertion error, which is a kind of exception. So assert raises an exception if the condition is false, but it's slightly different. And the reason it's slightly different from all of the other errors, value error, name error, etc., is that you're not actually supposed to catch it. So asserts are to make sure that the program is correct, not that the user is correct. So let me repeat that. Asserts are to ensure that the programmer is correct, not that the user is correct. What do I mean by that? So let's say you have some complicated function. What you use asserts for is to check that this function is implemented correctly, not that the inputs are valid. So here, you're checking the correctness of the function, not the validity of the inputs. So real root gives you some value, and so on. A test case looks like this. You're using test cases not to judge the user, but to judge yourself. So yeah, if your program is correct, your assertions are required or supposed to pass, except if you messed up somewhere. If you fail an assertion, that means you, as the programmer, messed up somewhere, not the user. So with that in mind, assertions should be invisible, or they shouldn't be relevant to the user. So why am I saying all of this? So let's say we have this function. Apparently it has a bug somewhere. So it's the fib function. Let me move on to assert. So I have a function over here. that does something like this. Okay, apparently it has a bug and we want to fix that bug. Okay, let us print fib of 5. Alright, we should expect, I think, 5 from this. So if I try to run assert.py, oh no, I get a recursion error. So apparently I'm exceeding the maximum recursion depth. That's not really good. So how do we fix something like this? Okay, what should you not do? First of all, don't try to panic and change random things. So you might change something like, maybe this should be 2 instead, and you check and it's still wrong. Maybe it's 3 instead. Oh no, it's still wrong. Maybe I should leave this out. Oh, it gives me something, but you're not always sure that the changes you made are right. In fact, you might have just made your solution even worse, which is what we actually did over here. Okay, you're never sure that the changes you make to your function are correct. So yeah, especially if your program is a lot larger than what this is, you might end up breaking an entire system or something, which is, well, not a good thing, I think. So yeah, analyze things carefully, make assumptions or predictions, and to make those assumptions, that is what you use assertions for. So let me go back to the less evil implementation of this. I think it was something like this. Okay, let's say we have a buggy program like this, and we want to fix it somehow. So in our fib function, one thing you expect out of it is that the input should always be at least 0, since 0 and 1 are the base cases, and everything else should reduce to either 0 or 1. So we can also predict that n must be at least 2 in the third case. If n must be at least 2. So in order to assert that or verify that, you put an assert n is at least 2 here. This is a sanity check to ensure that whatever is passing through this should always be at least equal to 2. So if I try to run that, oh no, it's an assertion error. So if we add an assertion and see that it fails, that gives us a big clue, since we know this is what we expect out of our working function, but our assertion is not passing. So we must have gone wrong somewhere. In other words, for some reason, n is becoming less than 2 when it reaches this line. So once you realize that, you can probably see, or you can try to see how it went wrong. So this is something I've demonstrated in the previous lectures. After an assert, you can print out whatever value you want, or more accurately, aside from just the assertion error, you can add a message to it. So here, if I run this again, I see assertion error, then 1. Okay, so if I want to make that more clear, I say I expected n to be at least 2, but I got whatever value I got instead. So here, if I run this, n must be at least 2, but I got 1 instead. Again, try to make use of this feature of assertions as much as possible, since it can be very helpful when debugging. Okay, so once you see that it's becoming 1, that's when you can probably start to realize that, yeah, you got n is equal to 1, but that's supposed to be a base case. So the only problem that can result to that is that you see here, that this n is equal to 2 should be n is equal to 1 instead, which is why this is getting a recursion error. So if we try to print that again, we see that it finally passes. Okay, so yeah, as you can see, by going through these steps, we've successfully debugged this faulty function over here. So yeah, we kind of did that in a systematic way. We thought of things that should be true in our function using assertions. And because of those assertions, we managed to see where our function went wrong. So try to make use of assertions as much as possible. We suggest just keeping these, don't comment them out, or just like how you would comment out a print or something, don't remove them. You don't need to remove them, since assertions are invisible anyway, and OJ is going to accept them. So you're not going to run into something like print is disallowed. Oh no. OJ is not going to complain if you use assertions, since we do encourage the use of assertions. Okay, so assertions, you can see that they're already useful now. They're going to be much more useful actually after the first hope, once we get into the second part of CS11. So yeah. Again, if there's something you'll take out of this section, assertions are for checking that the programmer is doing the right thing, not the user. Okay, so with that in mind, don't use assertions to judge the user. So if the user gives an invalid input, you're not supposed to use an assertion for that. Okay, let us have this example. So here I have this assertion, then this try except else. Okay, so here what I'm doing is that here, if the user inputs an invalid age, I have an assert. So let's say we run this python 3 assert.py. My name is Jerome, and if I input a normal age, I get the right result. If I do something illegal, we see that, well, since I catch the assertion, the error here, I just pass. So even though it's possible to do this, we really don't recommend it. Again, assertions are for judging yourself, the programmer, not the user. So instead of what we did there, use a normal exception instead. So if age is less than 0, raise a value error that's saying the age should be non-negative. So here if I print this instead, Daryl, then negative 21, it does essentially the same thing, but again, since we're using exceptions, that's better than using an assertion to force the user to do the right thing. Okay, so use assertions for the correctness of the program, not the correctness of the user. Okay, what have we been doing so far? We've been essentially debugging, or finding issues or mistakes in a program, especially with assertions. So debugging is the process of removing bugs or mistakes from your program. Debugging can be a very frustrating process, especially if you have no idea what's going on. But unfortunately, for all of us, debugging is usually unavoidable. Even for the most experienced programmers, debugging is still something that they do all of the time. So, yeah, we're all going to get stuck sometimes when debugging a program. What's important is not to panic, but stay calm and figure out where your program is going wrong. And again, we can do that using a lot of ways. We know that we can use assertions in order to verify the correctness of our solution. So in relation to assertions, we have this technique that we can use for making sure that our programs have as few bugs as possible. And we call that unit testing. Okay, so one way that you've probably been testing so far is, let me get a normal function over here. F of x, return x plus 1. Okay, one way you've probably been testing your functions is getting this whole thing, going to interactive mode, pasting the thing, then running it on inputs manually. So, well, I mean, this is certainly one way to do it, but it's not really that thorough. There are only so many test cases you can write if you use the interactive mode like this. So we're programmers and we want to automate stuff. That's mainly what programming is for. So for testing, we can use assertions instead. So testing can actually be done automatically. In a future lecture, once we unlock more dark arts or more features of Python, hopefully I can demonstrate some more ways we can test our programs. So yeah, testing can be done automatically. You've already seen that OJ is a good example of testing your programs automatically. All you have to do is submit, and it checks whether your solution is correct based on a set of test cases. So yeah, with enough experience, we can automate a large chunk of testing, and we will see this in a later lecture down the line. Okay, so the kind of programming that we've been doing so far, wishful thinking on different functions, this is amenable to a certain kind of testing. Since we're using or composing our program using several functions, we can actually test those functions separately. What do I mean by that? So let's say I have an increment function and I have a square function. If I want to test that both of these functions work, I can just write separate tests for them. So assert increment of 2 is equal to 3, 3 is equal to 4. Then for the square here, I can assert, for example, that square of 4 is equal to 16, square of 7 is 49, and so on. The point is, I can separate the assertions for this function from the assertions for this function. These are two totally separate sets of assertions. And that's the advantage of separating things into different functions. So unit testing. You're testing individual units or functions of your entire program. So yeah, usually you put all of the test cases at the bottom. You can either put all of them at the bottom, or after each function, put the unit tests for that function. I guess it's a matter of preference whether you want to put them, each set of them after their corresponding function, or if you want to put everything at the end like this. So there's no right or wrong really, as long as you're making assertions in the first place. Okay, so again, every time we run this now, Python 3 test.py, we see that these assertions run each time. So even if we add more functions to this and add more assertions, these assertions from a while ago are still there. So every time we run the program, we still run through these assertions. So our sanity checks are still there, no matter how big our program grows. So please use assertions as much as possible, even if you think they're ridiculously simple, like these functions over here. So that brings us to the question. We know we have to make unit tests, but what kind of unit tests should we be making in the first place? Okay, so the bulk of the effort of unit tests, how we test your programs on OJ for example, the main difficulty is actually designing a good test suite or a good set of test cases. When we say a good set of test cases, what do we mean by that? So first is your typical cases, like what we have over here. Just give it some relatively small inputs, then see that it works for those inputs. But also include edge cases. What do we mean by that? For square, one kind of edge case is if you give it a negative number, the result should still be positive, since the square of a negative number is a positive number. For string inputs, if for example you want to get a string and something like this, let's say I just add an exclamation point at the end. A typical or edge case for this is if the string is empty. So this should be just this. If it just has white space, it should be something like this. If it has special characters, then it should look something like this. So try to include as many non-typical cases as you can. Okay, so if for example in the constraints of OJ it says something like 1 is less than or equal to x is less than or equal to 10 raised to 5, try also to test your function on these big inputs, not just the small ones. So if I have cube of 10 raised to 5, this should be 10 raised to 15. So if I run all of those, that still passes. So don't just test on small cases, also test on bigger cases. So for string, include the empty string or even a ridiculously long string. So something like this. This should be equal to the same string with an exclamation point at the end. So if I run the test suite, all of these tests should still pass. Okay, so again, make sure to look at the constraints section and make cases as large as possible, depending on the constraints. Okay, so again, just because the small inputs work doesn't mean that it's going to work for all inputs. So don't just limit yourself to the examples on OJ. Try to make test cases of your own as well. So yeah, you need a different way of thinking when you're testing compared to when you're implementing. Try to be, I guess, the devil's advocate of yourself. So the programmer wants the program to work, while the tester wants it to break. So yeah, the tester has to come up with the weirdest or craziest test cases as possible. And yeah, try to form two separate parts of yourself when you're programming stuff like these. One that focuses on getting the function, implementing the function, and another one that focuses on trying to break the implementation. Yeah, so be a devil's advocate against yourself. So maybe in the review sessions for next week, I will go over concrete examples of how to do testing like this. But for now, for this lecture, this is pretty much all that we will go through. So again, let's try to recap. We went over input-output, exceptions and assertions. Again, for the nth time, exceptions are for judging the user, assertions are for judging the programmer. And unit testing. Make sure to include as many asserts as possible in your code, and as it says here, be your own devil's advocate. Don't always think that what you have already works. Make assertions a habit. So yeah, that is essentially this lecture. So again, please, I don't know how soon the hope is going to be while you're watching this video, but by then, hopefully you've practiced a lot by this point. Again, answer the check-in form for the week, and there are no corresponding readings for this lecture. So yeah, I am going to end there. So yeah, thank you for watching. This is going to be the last lecture before the first hope.